Okay, I'm just going to explain some tips and tricks about finding the pH of a weak acid. Alright, you pour 100 milliliters of a 0.45 molar acetic acid solution into an empty 250 milliliter beaker. What is the pH of this solution? Alright, so let's just start what we have. We have a picture of what's happening here. Okay, 0.45 molar of acetic acid in this beaker. Alright, so there's our equation, and then this Ka is 1.8 e negative 5. Alright, so our equation, there's our Ka. And so what you do is you write your ice table, right? Initial change equilibrium. And you'd say, okay, so it starts with 0.45 molar of this acetic acid, right? You start with that. That's your initial there. And you start with none of these two. And remember that water is a liquid, right? So it's not included in the equilibrium expression. So you can just cross that out entirely. Don't need to worry about that. Alright, so we start with 0.5 of that, 0 and 0 of that. Alright, so change. So we're just going to use x as our variable. So the change here is minus x, right? X molarity of this changes from this acetic acid into the acetate conjugate base. This will be plus x actually, plus x. And then also some hydronium ions, okay? And so finally we just add this together to get equilibrium. That'll be 0.45 minus x, the acetic acid, x for the acetate ion, and then also x for the hydronium. Alright, here's our ice table. So now let's enter it into the equilibrium expression. So we'll just write that out really quick. Right, so there's our equilibrium expression, and we're just going to plug in our numbers. So we have Ka's right here. That'll be 1.8 times 10 to the negative fifth. That's our Ka. Our acetate ion, which is this, will be x. So we're just going to write x for that. H2O is also x, so we'll write x. And then the acetic acid is 0.45 minus x. Okay. But here's where we use a little trick, right? And you've probably heard about this in your AP Chem class. But this is a little x problem, right? Because this Ka is so small, hardly any of this acetic acid is going to turn into these two ions, right? So most of it's going to stay as acetic acid. Therefore, this x is going to be super small compared to this 0.45, right? The x is going to be a much lower magnitude. So what we can do is we can say, if x is way smaller than 0.45, then we can just cross it right from out here entirely, okay? Because if x is way smaller than 0.45, then 0.45 minus x will just still be 0.45. So we can just completely ignore it in this subtraction here. But we have to leave it up here, alright? So that simplifies our equation like a lot. So now we have 1.8 times the negative fifth equals x times x, which will just be x squared, over 0.45, okay? So now it's pretty easy just to solve it. So let's do that. And then we solve for x. And so we just take the square root, and I'll just plug that in real quick. So I'll do 1.8 e negative 5 times 0.45, and I'll take the square root of that. And that gives me 2.8 times 10 to the negative third. Alright, I hope you got the same thing. So that will be x. That'll be the concentration of hydronium at equilibrium. And that's exactly what we want to use, so I'll write that actually. That'll be the concentration of hydronium at equilibrium. But we're not asked for that, we're asked for pH, right? So there's one more simple step that we have to do, because pH equals the negative log of hydronium, and we already know the hydronium at equilibrium. Just plug that in. Negative log 2.8 e negative 3 equals, plug that into our calculator. I got 2.55, okay? There we go, we've solved it. That's the pH of the solution at equilibrium. And as you can see, we wrote in our equation, we did our ice table, we plugged our numbers into our equilibrium expression, realized that we can use a little x here because it's way smaller than 0.45. And as you can see, this is a lot smaller than 0.45, you can ignore it. And then we just solve for x, and we solve for pH, alright? There's a way we can simplify this more, actually. And when you're doing chem lab, you don't really have time to write all this stuff out and do all these equilibrium expressions, these equations. You don't have time for that, because this is a very common question. So there's actually a shortcut equation that you can use that cuts this way down. It's way more efficient, alright? And we're just I'm gonna prove for you why this works real quick, and then you can use it comfortably. So let's just rewrite this equilibrium expression. And instead of using this, we're just gonna leave this as H3O plus, right? Because the concentration of this will be the same as the concentration of that, right? Because they're both gonna be x. So we're just gonna say, instead of those two things, we're gonna go right like this. Because these two will both be the same. And they'll both be equal to that. Alright, over, and we're going to make this general, not just for this case, alright? So what I wrote here is HA initial. So pretty much that just means the initial molarity of the acid. It doesn't have to be acetic acid, any acid. So that'll be like the 0.45 in this case, okay? And really what we've done here is we've already subtracted we've already done a little x, right? Because really on the bottom it should be HA initial minus H3O plus. But then we know that H3O plus is going to be so small compared to this that we're just going to simplify as HA initial, okay? From here we're just going to simplify a little bit. So we're going to say, alright, put this over here, we'll plug both sides by HA initial, and then I took the square root of both sides, and that gave me this, alright? Alright, so now what I'm going to do is I'm going to take the negative log of both sides. The negative log of H3O plus will just be what we're looking for, pH, right? That'll just be pH if I take the negative log of both sides. The negative log of this will just be the negative log of this. And this is our equation. pH equals negative log of the square root of Ka times HA initial. It seems a lot, but it's actually really simple to memorize. And it'll work for any weak acid where you can use the little x problem, okay? Anytime you can do that, you can just simplify, use this equation. Don't have to write any of this stuff out. Don't have to write any of the equal expression. Just literally plug it into this equation. And you can write this on tests, and they'll totally accept the answer. Okay, so let's just plug it. We'll plug our numbers into this and see if it gives us the same pH, and then we'll know it works. And so we're going to plug that into our equation, our calculator. So I encourage you to try that too. 1.8, negative 5, 4, 5. Right. And lo and behold, this also equals 2.55, the exact same pH that we got before. Didn't have to write out any equal expressions, didn't have to write any equations. Just plug it into this simple equation. pH equals negative log of the square root of Ka times HA. And that always works when it's a weak acid. Remember, it's a weak acid. It has to be a weak acid. And it has to obey B little x problem. Most problems you see on chem lab tests will be like this, will be weak acid and B little x problem. Alright, so now let's go into percent ionization. Alright, so it's actually a pretty simple equation. So percent ionization, you've probably seen it before. It's, alright, and then multiply by 100 to get a percentage. So let's just, we've already done all the math, so we can just plug these numbers in. A minus will be x, right? It'll be x, this x up here. So it'll be 2.8 e negative 3, and then HA will be 0.45, the one we've been using the whole time, times 100, and we get, let's do that. Alright. So you get 0.62%. That's the percentage of HA that turned into its ionized form. The important thing about percent ionization is there's this thing called the 5% rule. You may have heard of this, 5% rule. And pretty much this tells you if it can be a little x problem. If the percent ionization, if it's less than 5%, then okay, then you can treat it as a little x problem. You can treat this x as negligible, and you're allowed to cross it out, and then you can use this equation right here. Sometimes just looking at a problem like this, you wouldn't know. You're not totally sure if this is going to be 5% ionized. I kind of knew because this is a really low Ka, right? But it's not just based on like the percent ionization will also be based on the initial molarity and the Ka. But if you can look at the Ka and it's pretty small, then I'd say my general rule, if it's like if the Ka is less than this, 2.5 times 10 to the negative fourth, then you can generally assume you don't have to calculate percent ionization. You can just do a little x problem. If it's more than this, if it's like 7 times 10 to the negative fourth, or like 1.2 times 10 to the negative 3, unless it's a really high molarity, you won't be able to do the little x problem, and you're going to have to do use the quadratic formula. Yeah, 5% rule is that if the percent ionization is less than 5%, you can assume that the ionization is kind of negligible. You can treat it as a little x problem and use this equation. And that generally is associated with Ks that are between less than about like 5 times 10 to the negative fourth. If it's more than that, you probably can't use the little x problem.